Welcome to Module 47 in this series of lectures on statistical quality assurance and statistical process improvement. We're discussing so-called 2 to the p factorial experimentation and corresponding data analysis, really concentrating on data analysis at this point. And we're to the point of wanting to talk about what do we mean by effects in a so-called 2 to the p factorial study. And so we're going to begin as we did in two-way analyses or in two-factor studies by defining so-called main effects or fitted main effects. And these are going to be averages for y bars for one factor at a particular level minus the grand average y bar. So I, or the fitted main effect of factor A at level I, is going to be y bar average at that level of factor A minus grand average. Corresponding factor B fitted effect at level J is going to be a y bar for an average y bar for that level of factor B minus a grand average, and something similar for factor C. This is easiest to think about or see when one looks at this cube plot that we introduced in the previous discussion, the previous module. I want to talk about the main effect of factor A at its high or second level. What I'm going to do is average these four y bars, the ones on the right face of that cube, the ones where A is at factor A is at its second level. Factor A is at its second level, and then I'm going to subtract the grand average of these four plus these other four. Okay, so it's the ones on the right face minus the grand average. If you want to think about the grand average somehow sitting in the middle there, it's right face average minus grand average. The fitted effect of factor A at its low level is then, of course, the left face average of y bars minus the grand average. I wanted to talk about the main effect of factor B at its second or high level. That would be a top face average minus a grand average. The main effect of factor B at its low level would be a bottom face average of the y bars minus a grand average. And then finally, of course, the main effect of factor C, fitted main effect of factor C at its second or high level is a back face average minus a grand average, and the main effect of factor C at its low level or first level is a front face average minus a grand average. So as I've just illustrated here, that's the meaning of A2, there's the meaning of B2, there's the meaning of C2. By virtue of these definitions, fitted effects for any factor will add to zero. So A1 and A2 add to zero, B1 and B2 add to zero, C1 and C2 add to zero. That means that A2 is minus A1 or A1 is minus A2 and so on. Of course, I've just been talking in terms of a three-way factorial. If I had not three factors but four factors, A2 would be the average y bar for all combinations where A is at its second or high level minus the grand average y bar, and so on. So all of these ideas extend beyond three-way to higher-way factorials with 2 levels each. So you can see, if you go back to that cube, that the left face average is 52.75, the grand average is 64.25, that difference is minus 11.5, the right face average is 75.75 minus the grand average is positive 11.5, that is this guy and this guy total to 0. Put it differently, this thing's a sign switch away from that thing, and that holds good holds good for A main effects, B main effects, and C main effects. If one computes these things and looks at their relative magnitudes, the A main effects look to be bigger than the B or C main effects, and that is emblematic of the fact that the left to right differences on this cube seem to be bigger than the top to bottom differences or the front to back differences. So that's what the main effects are measuring. They're measuring face averages minus grand average, so they tell us about how this cube changes left to right, or top to bottom, or front to back. If I took the front face average minus the back face average, well, that would be A number 2 minus A number 1. So the difference between the face averages is a difference in the fitted effects. Okay, now how about two-way interactions in a three-way study? We've got main effects defined. How do we define two-way interactions? Well, there are at least a couple of ways to think about them. In the first place, if one thinks in a three-way study of averaging out one of the factors, so one could think about averaging the cube left to right, top to bottom, or front to back, leaving only 2 factors after one is done averaging. After one does that, you could think about, well, then if we make an interaction plot, do we have parallelism or not? So the point is that 2-factor interactions are measures of lack of parallelism that would be appropriate after averaging out over the other factor. Secondly, a different way to think about it is that ABIJ's 2-factor interaction of A and B at levels I and J are in some sense the difference between what you have for Y bars for a value for a level of A and a level of B, and sort of what you can explain in terms of a grand average A main effect and B main effect. ACIKs are differences between what is in terms of Y bar when you've averaged out over factor B, and what you can explain in terms, so there's a difference here. The point is that it's the difference between this and what's inside that set of parentheses, and that's in some sense an overall average, an A main effect, and a C main effect. That's what's explainable in terms of factors A and C acting separately. And these BC two-way interactions is the difference between what you can explain using the 2 factors acting jointly as compared to what you can explain with the two factors acting separately. It's a consequence that consequence of the definitions here, that interactions are gotten by that interactions, you can get them switching signs. And I realize here I'm missing a second letter. So think of this as AB11, AB12, AB21, and AB22. AB11, I switch one index from a 1 to a 2, so I have to change a sign. I go from here to there by changing one index, so I change the sign, and then I have to make two switches of indices to go from here to there, and so I get two. I switch signs twice, and I get back to where I started from. So again, sorry about this. Those should be ABs or ACs, depending on which one you want to talk about. I just I messed up the slides. In the pilot plant study, if you take, say, y bar 1 1 dot, okay, y bar 1 1 dot, that would be factor A at its low level, factor B at its low level, average out factor C. So it would be 60 plus 52 averaged. 60 plus 52 averaged is 56. And then if you subtract from 56 the grand average plus A number 1 plus B number 1, you get something fairly small. Okay, you get 0.75. So if I was to average front to back on that cube, what's being said there is that I had made plots of y bar ij dots. I'd have near parallelism on that plot, because this number and therefore the corresponding guys after I switch some of these indices from 1 to 2 are not very big. If I want to talk about AC interactions, well, that would correspond to taking this cube and collapsing it, averaging it top to bottom. So for example, if I want to talk about A at its low level, C at its low level, that would be y bar averaging 54 and 60, or an average of y bars 54 and 60. And average 54 and 60, you get 57. Subtract the grand average plus A at its low level, fitted A effect at its low level, fitted C effect at its low level, and you get 5, which is bigger than the 0.75. There's more lack of parallelism if I average out over B and then do some plotting of means than there is if I average out over C and then do some plotting of means. Finally, if I want to talk about BC interactions, so that would mean I'd take this cube and I'd average left to right. So for example, the average of 60 and 72, that's for B at its low level, C at its low level. So that would be for BC 1 1. That'd be 66 minus grand average plus B number 1 plus C number 1. That turns out to be exactly 0. And so that means that these other fitted interactions are also exactly 0. That says averaging left to right on that cube, you get perfect parallelism if you went about plotting the 4 corresponding y bars. There'd be no no lack of parallelism. So if one looks at factor A, low and high, level 1 of C, level 2 of C, so this is the plot for the AC, uh, for the plot where I've averaged out over B. Going back to these numbers, we see there's some fairly strong lack of parallelism there, and that is represented by the fact that these lines are clearly not parallel. Okay, so that leaves us with the problem of defining three-factor interactions or fitted three-factor interactions in a three-way study. And there are a couple of ways to think about this. The way I like the best really is to think of y bars, or what is in some sense, minus what is explainable in terms of all lower order effects. So a three-factor interaction is the difference between a y bar that has three subscripts on it and what is explainable in terms of an overall average, main effects, and two-factor interactions corresponding to that set of subscripts. In some sense, it's the difference between what's observed and what's explainable in terms of the factors acting separately and in pairs on this response. As it turns out, it's also the difference between what one would call two-factor interactions between A and B, looking separately at the levels of C. Okay, so if the point here is that if I took this plot and asked about, on the top here, asked about AC interactions, and then on the bottom asked about AC interactions. If I got the same interactions on the bottom, AC interactions, as I got on the top for AC interactions, then that would mean that there is a three-factor interaction involving factor B. So that is that's what I've said here in this part of the slide. Three-factor interactions sum to zero over all levels of any of the factors, so you can compute one of them and get all the rest by appropriate sign changes. So if I wanted ABC 111, I take y bar 111, subtract a grand average y bar, an A1, a B1, a C1, an AB11, an AC11, and a BC11. That turns out to be minus 0.25, and then I can go from that to any other fitted three-factor interaction by just making sign changes. So if I want to go from this to ABC 112, that involves one sign change, so I go from a minus sign to a plus sign. To go from 111 to 112, that involves two changes of indices. That's two sign changes, and I'm right back where I started. Interpreting three-factor interactions is more difficult than interpreting two-factor interactions. Happily, in this study, these things are small in comparison, say, to the main effects, to the two-factor interactions. Truth of the matter is, if you're doing a p-factor study or you're analyzing a p-factor study, if you've got large high-order interactions, then chances are you're not going to be able to find sensible interpretations, or it's going to be more difficult to find sensible interpretations, and you may just have to go back to treating the combinations of the levels of the factors as just some number of ways to make combinations.